All right, let's get right into it. Today, we're going to pull back the curtain on one of the most fundamental ideas in programming, the list. It's the digital blueprint that organizes, well, pretty much everything in our modern world.
I mean, seriously, have you ever stopped to think about it? Every time you add a song to a playlist, save a new contact, or just check something off your to-do list, you're using a list. But how does your phone actually manage all of that and keep everything in order?
Okay, so before we dive into the nitty-gritty, we gotta start with the big picture, the user manual, if you will. In the world of programming, this is called an abstract data type, or ADT for short. Just think of it like a contract. It tells us what we're allowed to do with a list, like add stuff or remove stuff, but it completely hides all the complicated details of how the computer is actually making it happen.
So what's in this contract? What are these rules? What are the commands that the list promises it will understand?
Well, this contract gives us a basic vocabulary. We get these simple, powerful commands. We can append to add something to the very end, or prepend to stick it at the beginning. We can remove an item from anywhere in the list. And we can even ask it questions, like, hey list, do you contain the number 99? Or how many items are you holding right now? These are the guaranteed actions.
Let's see this in action with a super simple story. We start a new list called ages. First, we append 55. Then we append 88, then 66. Now notice how the order is always preserved. Each new item just gets tacked on to the end. But now watch this. When we say to remove 88 from the middle, the list just seamlessly closes the gap, keeping the others, 55 and 66, in their original order. Pretty slick, right?
Okay, so we've seen the rules from the user manual. Now it's time for the fun part. Let's peek behind the curtain and look at one of the most common blueprints engineers use to actually build a list. So how does it really work? How does the computer keep that order so perfectly, especially when we do tricky things like removing items right from the middle? Well, the answer lies in this really clever structure called a linked list. The fundamental building block, the secret ingredient of a linked list, is something called a node. And honestly, it's incredibly simple. A node is just a little package, a container that holds exactly two things. First, the actual data you care about, like the number 55, and second, a special pointer. You can just think of a pointer as a digital address that tells the computer where to find the very next node in the chain.
The treasure hunt analogy is absolutely perfect here. See, each node doesn't know about the whole list, not at all. It only knows about its own piece of treasure, the data, and where the next clue is hidden. That's the pointer. By following these pointers from one clue to the next, the computer can trace the entire list from start to finish.
Now, to manage this whole treasure hunt, the computer only needs to keep track of two special addresses. First, the head, which is just the pointer to the very first node, the start of the trail. And second, the tail, which is the pointer to the very last one. If you know where the list starts and where it ends, you can control the whole thing.
And here is the whole thing put together. You can see the list's head pointer kicks off the chain, pointing to that first node holding the number 32. That node's next pointer then leads us right to the node with 64, and that one points to the next, and so on until we hit the very last node. Its pointer just points to none, which is the signal for we're at the end of the line. And that tail pointer, that's just a handy shortcut that takes us directly to that last node.
So that's the structure. But how do we actually modify this chain? How do we add or remove links? This right here is where the linked list design really starts to shine. Okay, let's look at this super simple list of ticket numbers. We just have 2496. The head points to the start, node 24, and the tail points to the end, node 96. Easy enough.
Our goal is simple. We want to append the number 70. We want to stick it right on the end of this list. So, how do we do that by just messing with pointers?
It's a really quick two-step dance. First, we go to the current last node, number 96, and we tell it, hey, your next pointer shouldn't be empty anymore. It needs to point to our new node, 70. Then for step 2, we update the list's main tail pointer so that it knows that node 70 is the new end of the line.
And boom, just like that, it's done. Node 96 now points to our new node 70, and the list's overall tail pointer now also points to 70. We've successfully added an item to the list, and notice we didn't have to move or shuffle any of the original data around. It's super efficient.
Okay, adding to the end is one thing, but what about yanking something out from the middle? In some systems, this is a real headache, but for a linked list, it's actually pretty elegant. Here's a list with 55, 12, and 74.
Our mission:
should we choose to accept it, is to remove that node with the number 12, which is sandwiched right there between 55 and 74. Now, the logic here is just brilliant. We don't actually delete the node for 12. Instead, we just make the list forget it even exists. We go to the node right before it, in this case node 55, and we just rewire its next pointer. Instead of pointing to 12, we tell it to just skip right over 12 and point directly to 74 instead.
And there you have it. The chain now flows directly from 55 to 74. Now that node 12 might still be floating around in the computer's memory for a millisecond, but it's no longer part of our list. It's been cut out of the chain, effectively and efficiently removed from the sequence.
Okay, so let's just take a step back for a second. We've seen the simple commands, and we've seen all the complex pointer magic happening underneath. Let's connect these two big ideas together.
This slide right here, this gets to the absolute heart of it all. As a user of the list, all you need to care about is one simple, readable command: list.append item. That's it. But as the implementer, the engineer who built the list, you know that that one simple command actually triggers a whole multi-step process of reassigning pointers. This is the crucial difference between the what we want to do and the how it gets done.
And this powerful separation has a name. It's called abstraction. And it's probably one of the most important concepts in all of computer science. It's what allows us to build incredibly complex systems by relying on simple rules and contracts, without getting bogged down in the messy details of every little component. It lets you drive a car without needing to be a mechanic. It really is a programmer's superpower.
So this linked list blueprint is clever, right? It's incredibly efficient for adding and removing items, but it's not perfect. What if you wanted to jump instantly to the 500th song in a massive playlist? Following 499 pointers one by one could be, well, pretty slow. So what are the trade-offs of this design? And what other blueprints could a programmer choose from to build a list?